So, hi everyone, and welcome. My name is Giulia Guizzardi. I think a little bit of you know me already. I'm on the community team at the DFINITY Foundation. Today we're here for our 5th workshop, and the topic is Build an Encrypted Nodes Dapp. And our speaker here is Dr. Arshavir Ter-Gabrielyan, who is a software engineer in the testing and verification team at the DFINITY Foundation, obviously. He's going to kick things off with the workshop, and I will be monitoring the chat. And please use, I ask you, please use the Q&A function that you find on the bottom of the Zoom to ask questions. Arshavir told me he would like for the session to be interactive. So if you have any question, we would go through them while we're going, but we also will collect some of them for the end. And the workshop is being recorded and I think also live streamed. I'm not sure, but I think so. And it's going to be posted on the DFINITY YouTube channel in the following days, probably Thursday. So without further ado, I'm going to hand it off to Arshavir. So feel free to take it away.
Thanks for the kind introduction, Julia, and hello, everyone. So the goal of today's session is to present one of the example dapps that we at DFINITY have developed in such a way that it showcases some interesting aspects of building dapps on the IC, and does that both in the Motoko and the Rust ecosystems, so you can choose which one of those you prefer, but you can also compare how different things are achieved in the 2 languages that we support at the moment. So first of all, let me give you a quick intro into the idea of this dapp. Of course, in every dapp, there has to be a user, and in our scenario, this user is going to connect to the IC using a device onto which it can go to a front end, which could be a web browser, for instance, and enter the user interface of our dapp. That would look a bit like this. So from the name of the dapp, encrypted nodes, you can already know that the purpose of it is to be able to take nodes and store them in an encrypted and secure fashion on the IC. So the backend of the dapp is actually a canister smart contract running on the internet computer.
Arshavir, you're not sharing your screen. I don't know if you were supposed to.
Just a moment, please.
Yeah, no worries.
Yes, indeed. The user, the device, and the front end that I wanted to show to you, and this depicts the canister smart contract that is writing that is working on top of the internet computer. So the key aspect which makes these nodes encrypted is that the front end does not have to trust how the canister is implemented and can store data in a secure way because it encrypts it at the client side. So then only the encrypted data is actually stored on the IC. And in addition to this, an important feature of the dapp is that it supports the use case of multiple devices per user. So for instance, if we have a laptop and a couple of cell phones or other gadgets, then all of them should be synchronized. So the encrypted nodes on all of them should also synchronize. And of course, since there are multiple users, then we have a situation like this. All of the data has to be stored per user in the encrypted nodes canister. So the first design decision that we make here is to use the internet identity canister, which is a different canister that already provides the authentication functionality to us, and we use it as an external service. It also runs on the IC and grants authentication to our encrypted nodes Dapp. And to give you a slightly more in-depth overview of how the backend is organized, so we'll go into more details about it later into the session. But the most important aspects are that nodes are stored by their node identifiers, which are implemented as natural numbers in terms of the Motoko implementation. And they're hashed by user and by node ID. Okay? So, for example, if Alice here has a list of devices, and each of these devices will be represented in the internal state of the canister via a public key of that device, which is depicted in orange. And at the same time, we will have the shared secrets, which we also need to store in the canister, that will correspondingly be organized in the internal state of the canister per device. So what this achieves is a way of synchronizing devices in a secure manner that I will demonstrate to you in a moment. So now I'm going to enter a web browser, use it as one of our devices. So this canister is already deployed to the mainnet, which means that it's accessible through this address over here. And in order to use it, the user would need to first authenticate. And this is the part where our interface redirects us to the internet identity canister. And here, I'm going to click Authenticate and use my existing identity, as well as a hardware token, in order to confirm the authentication and proceed. Now we're redirected back to the encrypted nodes canister, which is processing our authentication request, which takes a bit of time because, of course, all of this runs on chain. And here, what we see is the user interface of our Dapp. So if I extend the window a little bit, you will see all of the functionality, all of the basic functionality that we currently support. In particular, I can add nodes here by clicking Add Node. Also support more advanced features, such as tags that we can attach to our nodes. And then we can navigate from this editing window into your nodes interface. And then we see all of the nodes that have been taken by us, by this user. And then we can edit them if we wish so. For instance, I can remove this tag and save it again. Now, this is not so interesting yet. However, let's see how the device synchronization feature would work. So in order to demo this part, I'm going to use another web browser to simulate a different device through which I can also authenticate into the encrypted nodes Dapp. For that purpose, I'm navigating to the same URL. And here, since I have to admit that I don't remember my internet identity, I will first have to log out from this device and then log in again to be able to copy paste my internet identity and then use it on both of these devices using my hardware token. So now you see that there is a synchronization phase in which the list of devices that is associated with my identity is being extended. And this is where the shared secret is being synchronized. So here, if I navigate to the devices list, then I will now see that there are 2 of these. Although we do not currently support specifying your custom aliases for these, it is nonetheless possible to see that the automatically generated identifiers actually match 2 of our devices. So here, this one is the bottom one, and on the right, we have the top device. Now, a feature that we have access to from this interface is the device removal feature. So if I hit remove device, then ultimately we will see that the left device has been logged out. And this shows that you can remove the device. So, but here, let me associate this device with the same identity once more. And actually explore whether the nodes have been synchronized across the 2 devices. So if you remember, we had 2 nodes that we created. And what I'm going to do, I'm going to navigate to the list of nodes on the other device. So you see that in my Firefox browser, I also see these nodes, and I can edit them. And click Save. After which you see that the change has been propagated to the device, to the right device. And similarly, if we now try to remove one of the nodes, then of course we should observe this change in all of our synchronized devices. Let's see if this indeed happens. Okay, the node has been deleted successfully, and as you can observe, we got this change propagated also to our left device. So I see that there may be some questions in the chat at this point. Oh no, not yet. Just welcoming.
No, not yet. I will. Do we have some question from our attendant? There is a. Oh, there is a hands up. Yvonne? Yvonne, do you want to ask your question?
I don't want to ask a question.
Oh, sorry. So we have another question. How do you know it's encrypted, from Mark?
Right. So that's a very good question, because if we return to the architecture overview, let me just bring it back to the screen here. Then what you see is that the encryption part is a feature of the front end. Let me zoom in a little bit. So encryption is a feature of the front end itself. And what this means is that you could see this as the client having the possibility of using our dapps in a secure in a secure fashion. However, the backend does not check whether the information stored in the canister is indeed encrypted, right? So to a certain extent, any DApp consists of a front end and a backend. And here the design choice to perform encryption is to do so only on the front-end side. And the reason for this is that then the client does not need to trust the backend, that the backend would perform such an encryption, right? And the fact that the front end performs encryption could be checked because, of course, the front end source code is open. So before using the Dapp, one could, in principle, explore what it does. And this allows us to say, well, at least from the perspective of the front end, the content is indeed encrypted because it's being encrypted and decrypted only at the front end side.
We have a couple of more questions in the Q&A. One is from Byron that says, what are you using to pull on the front end?
To do what? Sorry?
Pull. I don't know if it's a technical term or if Byron wants to explain better.
Yeah, maybe this is coming from the way we designed polling. So the front end is actually polling for changes. So,
okay, he explained to receive updates but between devices.
Mm-hmm. Exactly. So the front end is polling our backend canister from time to time in order to detect the moment when there are new devices that have to be synchronized. And I can show you a sequence diagram for a device synchronization process in a moment. And maybe that would be helpful to answer your question more precisely. Just a second, please. Right. So this is the smartcontracts.org website where we have a documentation for the Dapp, a high-level documentation, which also contains this sequence diagram, although it's a bit, I think it's going to be a bit small. The font is going to be a bit small for you, but if you navigate here, there's an encrypted notes section that covers the device synchronization sequence. And here you can see that an existing device is polling for unsynced devices. And then if it detects that there have been new public keys associated with new devices that are added to the backend canister, then it performs encryption of the shared secret with the public key of the new device and submits the encrypted shared secret, after which other devices are going to also poll for the encrypted shared secret and propagate the change in this way. Yeah, thanks, Matthias, for sharing the link into the chat. Are there any more questions at this point?
Yeah, there is another one from Fabio that says, the reason why you added an encryption in the Dapp itself is because canister's private variables are not secure. If yes, who can access it in it other than the canister owner?
Well, actually, it's a very good question. So the thing is that the data stored in the canister is secure. However, it's not confidential. So to achieve confidentiality, we would not need to trust even the developers of the canister. Because otherwise, we could have a situation in which somebody deploys a Dapp onto the IC, promising certain services and guarantees and properties for the users. And then at another point in time, they can upgrade the canister, which is one of the features of the IC that makes it a viable platform for building your dapps. that you can actually upgrade the canisters quite easily. But then how do you know that even if it used to be the case that your data has been secure and confidential, that that's still the case after an upgrade? And in order to not be required to trust the backend, the encryption can be done at the front end side. But to some extent, this is a design choice that is specific to the use case of encrypted nodes. It could be that for some other services that are not open to the general public or to anyone who has access to the internet identity, they could perform encryption at the backend side. But then you would need other means to be able to ensure properties of your data, such as privacy. I hope that answers the question. And I see that there's another question. Can a developer just deploy a different front-end canister without encryption than without the users knowing? Yeah, so the users cannot control when the canister is being upgraded. So the data that you store in a canister, it's a good idea to encrypt it at the client side for this very purpose, for this very reason. However, the code of the canister, of course, it can be certified, and different concrete scenarios of doing so are being considered at the DFINITY Foundation as potential future features that we will offer to the community. But as of today, in order to trust a Dapp that is deployed to the IC, it's a good idea to explore its source code, but also to be sure that you're using a trusted front end that performs the necessary encryption, maintaining the desired properties of your user's data, such as privacy. So another question from Pat: could there also be memory reading attacks when having physical access to IC nodes? Yeah. I'm not sure I understand what physical access to IC node. So I'm not sure I am understanding what scenario this covers. Maybe could you make the question a bit more specific? However, I will say that there's been a security review in-house for our example dapps, and many of the findings have resulted in us developing guidelines for how secure dapps for the IC could or should be developed. And if you go to the example dapp repository, then you will find in the Motoko section, actually, you will find the encrypted nodes dapp together with the security checklist file. So let me see if I can visualize this a bit better. Okay. So here you will see many of the security concerns that we have considered, or maybe we purposefully have not addressed them for the purpose of this example dapp, but they're still mentioned here. For example, canister upgrades or Rust-specific issues, and so on. So I think that a lot of the questions that you're having are going to be addressed by this document to some extent. At least they might be mentioned there. So please take a look.
We have actually another question, but I don't know if you want to go on and then maybe answer later, or you want to answer now.
Right. So for the physical data center access, maybe I'll briefly tell you my thoughts on that one. I think the point of building dapps on the IC, or at least one of the advantages, is that there's not going to be a single data center that one would need to attack in order to get to gain control over a canister, because it's deployed to an entire subnet. And this means that there is additional security that comes from the fact that a subnet consists of nodes that are typically within multiple different data centers. So maybe last question from Byron Becker. So how can I verify the front-end canister code I'm looking at in the browser belongs to a certain commit in the repository? So this, is it the developer to make that information public? Is it up to the developer to make this information public? So that's a great question. I think that one of the features that is being prepared at the DFINITY Foundation is going to address this very issue to make it more accessible for developers to certify their canisters. However, I'm not going to go into the details on this one. So I think for the remaining time, it would make sense if we explore the code base of this Dapp a little bit more closely. So thank you for the questions so far, and please feel free to submit more, and I will try to have time to answer them at the end. So first of all, in order to deploy this Dapp, you can look into the instructions from the README file, which are quite detailed. And we will not repeat all these processes, but it has a high-level overview, and most importantly, it has the concrete steps that you need to be able to deploy our encrypted nodes Dapp locally and be able to run tests or to develop against your local deployment. Effectively, it's done using a single bash script, which is internally calling Docker. So it's a Dockerized deployment solution. But there is also a way to deploy it locally without Docker, if that's what you want. For instance, this is what we use in our CI pipelines in the DFINITY example dapps repository. So if you want to play with this Dapp, maybe change it in some way, and then get the changes deployed, then the README file is your first point of contact. So now a few words about how the repo is organized. Here in the SRC subdirectory, we have encrypted nodes Motoko and encrypted nodes Rust. I will only explore the Motoko part because if you have specific questions for Rust, then we can also go into that, but I don't want to spend too much time on that for this session. And then there's a subdirectory called frontend. So in the frontend, we have our frontend, which is literally the thing that you've seen in my web browser. And this is written in the Svelte framework, right? Using TypeScript, CSS, and HTML kind of technologies that you're probably familiar with. But the thing that is most interesting for us is to see how the canister itself is implemented. And for that purpose, I'm going to navigate to main.mo, which is the entry point for our canister. So here I'm going to be assuming that you have some knowledge of the Motoko language, but or at least you are familiar with concepts such as actor classes. But feel free to ask questions if something is unclear from what I'm saying. So in this file, we define the one and only actor class that implements the encrypted node Dapp. Okay, that's not entirely true because as I mentioned, the Internet Identity Canister is an independent service, which is also part of this Dapp in a way, although it's an external service. the first thing that we do, we declare certain constants. Now, this is a very important point in practice, because for any DApp that you're deploying to the IC and that is going to be accessible to a potentially huge set of different users from multiple different devices, you want to set bounds on certain parameters of your DApp. And here we do this for multiple reasons, but most importantly for keeping the DApp secure. For instance, making sure that it doesn't run out of memory or out of cycles. And for that purpose, we specify the maximal number of users at 1,000, for instance. And we specify the other constraints in such a way that we do not exceed the constraints that we have for, or the memory limits that originate from the limitations of WebAssembly. Keep in mind that these limitations change. So you might get more memory per canister, but in a practical scenario, if you're running out of memory in one actor, then of course you can deploy multiple actors that then would need to communicate with each other. And then this way you can effectively implement the sharding pattern using actor class. So after these constraints that we set, there's a type of principal name. And for that purpose, we use text, which is a built-in type. How do we know it's built in? Well, because it's in the standard Motoko library, starting with MO, right? And now let me go through the rest of the fields or types that we're going to use. The encrypted note type is a simple structure with two fields, with an encrypted text and an identifier, which is a natural number. Now, an interesting, important point here is that although the variable is called encrypted text, there's no encryption that is actually performed by this actor. So here, this is just for us to for the developers of the canister to remember that this value is supposed to contain encrypted text. But of course, the user should not trust that this is always the case, and hence they should perform encryption at the front-end side. Now, the next field here is the next node ID, which is serving two purposes. So on the one hand, this is a counter that we use to generate new unique node identifiers. And these are supposed to be globally unique, which means that if we create multiple nodes and then delete some of the nodes and then create more nodes, we never reuse the node identifiers. And this is an implementation detail. It could be done in a different way as part of the design. And then we have a field called nodes by user. So this is effectively a map from principal name to a list of encrypted nodes that is associated with that particular principal name. So a principal name is something that identifies a Dapp user, right? And this list is the buffer that contains the encrypted nodes of that user. So here, one aspect of the design that I would like to mention is that we did not aim for creating the most efficient or the most secure Dapp, because in practice, achieving these goals is very, very difficult. However, what we wanted to do is to showcase how different things could be done in a realistic setting. So here, although we store the nodes in a list, and this is not the most efficient data structure, one could argue for storing this data, it does allow us to show how these structures or data types could be used in the Motoko language. Next up, we have a variable called nodes by user with the prefix stable. So this is what we use in order to support upgrade scenarios. If you're not familiar with this, there's a nice website, there's a nice page on smartcontracts.org that covers what canisters upgrades are and how they can be achieved in a secure manner for canister developers. I'm not going to go into too many details there. However, the raw idea is that we have some data structures which are more efficient, such as a hash map. So it allows us to access data slightly more efficiently than if we had to iterate, through the entire structure. But this is not a stable type in the sense of the Motoko language, which means that it cannot be automatically persisted across canister upgrades. And this is a very important practical issue, because if you're going to deploy a distributed application as a service to your users, you definitely don't want to lose your user base each time you're upgrading, right? And the users definitely do not want to lose all their data. So for that purpose, we will use canister upgrade hooks that we will implement all the way down here. So I'm only briefly going to mention how these work. Before a canister upgrade is performed, the pre-upgrade system function is being called. And the purpose of this function is to take our more efficient but unstable data structures and convert them or serialize them into stable types that we can persist across the updates. So this is going to be the buffer that stores nodes by user, the information that is normally stored in the variable called nodes by user. And then after a canister upgrade, the system function called post-upgrade, which is a special function in Motoko, is going to be invoked. And the dual purpose of this function is to deserialize from our stable representation that is stored in these stable prefixed variables and buffers into our original, more efficient data structure. So that's how it works. Keep in mind that in practice, canister developers would benefit from using stable types as much as possible, because if you can use a stable type for your buffer, you don't need to manually serialize it and deserialize it upon canister upgrades. So you might implement a Dapp in Motoko that doesn't even require explicit upgrade hooks to be written. It will happen automatically by the language if you use only stable types. So if you can organize your data structures in such a way that all types are stable, then you would benefit from this simplicity. Okay, returning to the fields, the last, or actually not the last, but the next important field is the collection of users, all users of our Dapp. Again, this is a hash map that hashes, well, that maps principals of the users to elements of the type called user store. And we have the corresponding stable version of the same container. Now, a couple of words about how we perform dynamic checking for the properties of this canister that we care about. It's quite important to be able to phrase certain invariants that your actor classes should maintain. For example, since we're using two different collections for storing users and for storing user nodes, we need to maintain the property that the sizes of these two maps are actually equal. So they have the same number of keys. And this is an example property that in our implementation, we check in various places. But for instance, each time that somebody asks for the user count, we check this invariant, because in principle, it could be computed either of these ways. So we need to make sure that it's synchronized. So there are a few functions, and I'm not going to go into each and every one of them, but only in those that I think are most interesting to look into. So this is another example that shows how we can check certain properties, namely that the identifier of a node is same, which puts it in a range from 0 to some big constant. But since natural numbers in Motoko are unbounded, it is possible to have an arbitrarily large number, specified as an argument of an API call to the canister. And therefore, we need to be able to perform these checks to reject those which are definitely inaccurate or wrong. So if we go into one of the examples where we use this isID same function, we will get a better illustration of what I just said. I'm going to navigate through this one more function and then address the questions that we already have. So this update node function is one of the public API functions that this actor exposes, and hence it has the following features. It has the keyword public. The return type of this function is a async value. And finally, it specifies the caller parameter. So the caller, you can think of it as another actor in your system that has some principal. And the first thing that we do is we check that this principal is not the anonymous principal. So what this means is we're not allowing anonymous users to use the Dapp. If you want to use the Dapp as a user, you must authenticate yourself such that your principal is not the same as the reserved one for the anonymous user. The second thing that we do is we check that the user, that the caller is a registered user. And how do we do that? Well, let's navigate to this user registered function, which is implemented in a very simple way. If this principal exists as a key in the user's hash map, then we know that this user has been registered. So I think we'll stop here. The next precondition in this function that we're checking is that the number of encrypted texts. Is that the size of the encrypted text of this encrypted node that we have as the parameter is within the bounds. Effectively, it's small enough. And finally, we check that the identifier in this encrypted node, that is an argument of our update node function, is actually say. So performing these preconditions or checking these preconditions is essential in practice, because this is how we achieve security. We should, as canister developers, we should always assume that somebody could be implementing a malicious front end that would not purposefully try to be the protocol, or maybe there will be bugs on the front end side, and we need to compensate for that at the front end. At the backend side too. Hence, all of these checks are performed as the precondition of this public API function, as we do for the other public API functions as well. Okay, then what else is happening here? So the actual business logic of this function is that we check that the nodes by user for this principal name already existed, and expect is a way of asserting that there was some value here, and otherwise we raise an exceptional situation and the canister traps. Now, a brief note worth mentioning is that canister traps are normal and secure canister behavior in the sense that the state of the canister is going to return to the same state that it had before invoking this public API function if it traps. So this means that it's easier to design secure dapps because you don't have to handle exceptions in a way that you manually roll back to the state that you had, make sure that nothing has been, no properties have been violated. But this is something that the language does for you. And then once we get the existing nodes, we map them using this anonymous function over here. So what it does is for each encrypted node that this user had, we perform the following comparison. If its identifier is actually equal to the identifier of our encrypted node parameter, this means that we found the node that is supposed to be updated. So we return the updated node, and otherwise, this means that this is not one of the nodes, or not the node that we want to update. And so we return the old node that we already had. And finally, after performing this map, we store the newly created list of user nodes under the same principal name in our nodes by user collection. So this is an overview of one of the public API functions. And now maybe it's worth just showing you what the API actually looks like, top to bottom, because we won't have time to go through each and every method in the API, unfortunately. But so for the Motoko version, we have implemented the same API as we have for our Rust version of the canister. Those are two alternatives, right? And therefore, the candid specification of the API is also exactly the same. So here you can see that the functions that our service supports are these. There's an add node, delete node, get nodes, get ciphertext, get devices, get unsynced pub keys. This is the one that the frontend is polling for. Is seeded, register device, remove device, seed, submit ciphertexts, update node. And just for debug purposes, we also have a who am I, which effectively returns the principal of whatever actor has invoked this public API function. So as you can see, there's not a very large list of publicly available functions, but these are sufficient for implementing our use case. And in addition to these functions, there's also a few candid types that we have at the level of the public API. Namely, the result is a variant with a potential error or potentially okay. Public keys are effectively the same type as text. Get ciphertext error is a type that returns this variant over here. then most importantly, encrypted node is a record that has two fields, an encrypted text and an ID. And this corresponds to what we discussed on the Motoko level. And finally, there's a device alias and ciphertext, which are both equal to text, and the service. So this is just a boilerplate that we typically have in our candidate specification. So as you can see, the specification is not incredibly complicated.
Hey, Arshavir,
Hopefully,
sorry to interrupt you. Be mindful of time. It's only 5 minutes remaining. Do you want to have a look at the question, or do you want to finish your thoughts?
Yeah, thanks for the heads up, Julia. So I think we're basically done with a very high level overview of the Motoko implementation of the encrypted node step. And so let's take a couple of questions. So I see that there's 4 open. Do you want to read them?
Yeah, there's one from Brian. Is there a website that has ready-to-use data? An example, let's say I want to use Google Maps in my canister. Is that safe to use? Or if I want to have some data, like about businesses address, what I can use?
Mm-hmm. Yeah, so that's an interesting question, and I think the specifics would be very important to figure out to be able to answer it precisely. I think currently there's no such website. The thing is, it depends what trust even means, right? How we define this notion, and part of the reason to use a platform such as Internet Computer is that you don't trust just one party. You want to avoid trusting just one party. You want to have, consensus-based trust, right? And if you go that route, then probably you don't want to have a single website that certifies or that you would consider trusting or not, because trust is a thing that could change in time as well. So that's something that needs to be figured out in the future, how we do this in a distributed fashion. Hope that helps. So Fabia has a question too.
Mm-hmm.
How much a canister is scalable, I suppose? Like for this DApp, which could be the limits in terms of users' nodes stored before having slow responses, or reading the list of nodes, or for writing new nodes? Okay, very good question. So I think performance-wise, the bad news is currently it's, as you have explored, it's a couple of seconds of delay before you can authenticate or synchronize your devices, because this is happening on chain. The good news is that the scalability limitations do not come from the performance side, but mostly come from the side of engineering your canisters in such a way that you would overcome limitations of WebAssembly. So this brings us back to the discussion of, if you have too much data for a single Motoko actor, then you can implement more advanced schemes such as sharding in order to cover your more advanced use case. For instance, if you would like to implement an entire database using the Internet Computer as a backend. So it's possible, but there's more engineering involved. Then a question from Fabio: the pre and post upgrade used are from the new version or from the old version? For example, if we have v.1 that tells post upgrade to print A, and the v.2 that we are deploying tells the canister to print B as a post upgrade, what would be printed? Yeah, it's an interesting question. What happens if you change the upgrade hooks? Actually, I don't know the answer to this question. Sorry, but it's an interesting question. So I would recommend asking it in the forum. if this is something that you practically hit. I suspect that it would be good if you don't have to change the upgrade hooks too much. So there's definitely something that you should plan ahead of time when designing an IC canister in such a way that then it's easier to make it upgradable. Okay, then there's a question from Mikhail Turilin. Is there a concept of database on the IC? Or are data stored in the agents list and hash maps? There's no databases, and that's one of the advantages of the IC, that you use persistent data structures, which are the same kind of structures that your language supports natively. So for developing small applications, this is much easier to use. However, of course, if you have more ambitious applications in mind, then you have to design not databases, but effectively sharding protocols for your data structures across multiple actors. Okay, sorry, we ran out of time, so I didn't have time to answer all the remaining questions, but I think these pretty much cover it. So thank you very much.
Yeah, Arshavir, thank you so much. You've done such a good job explaining this really complex topic, at least for me. And thank you everyone for so many interesting questions and really investigative questions. I shared in the chat the dev forum. Maybe we can keep the conversation going there, asking questions and understanding also what the other members of the community are actually answering to those. And yeah, thank you again, Arshavir. Thank you to everyone for participating. It was really nice having you all here. And yeah, we'll see. If you want to see the recording, you're gonna see it on Thursday on the YouTube channel, and also if you want to see the other episodes and the other webinars episodes, yeah, as well. Okay, thank you all. Bye.